So this video, we're going to be looking at free body diagrams, which are the most important picture that you will learn to draw in this course. So they deserve a little smiley face beside them here. Free body diagrams are awesome, and they'll be so helpful to you throughout your physics career. So for a free body diagram, what we're looking at is all of the forces on an object. So the first thing you need to know is what is your object that you're drawing a free body diagram of. Maybe my object is a car, say, or my object is myself, and I'm drawing all the forces on that object. Be really careful about what those forces are. So you're going to draw all and only the external forces that your object feels. So say my object is a car has all kinds of internal forces, right? The engine is pushing on stuff, there's the axles pushing on the wheels, right? There's tons of different internal forces inside the car. But the force of the engine is not an external force pushing on the car. That's from within the car. So we do not draw that force on the car. You're only going to look at the surroundings, see, well, what forces is the surroundings exerting on my object? Those are the forces that go on your free body diagram. The other piece is that you're looking specifically forces on the object, not forces that the object exerts on its surroundings. So let's say you're doing a free body diagram of me, and I'm pushing a stroller with Clara in it. As I'm pushing the stroller, I'm exerting a force on the stroller, right? But that free body diagram doesn't show up on that force doesn't show up on a free body diagram of me. I can only draw forces that I feel. The force that I exert on my surroundings is not a force that I would draw on this free body diagram. So be really careful about that. So your first goal is to figure out what are the external forces that my object feels. Once you know what those external forces are, you're going to draw the tail of each force, starting at the object, and then traveling in the direction that that force pulls or pushes. So this would be a force pushing my object forwards. Notice that I don't draw it like this. So if I have an object here and I'm pushing on it, I would not draw the force sort of pushing at it like that. That would be wrong. You would draw the force starting on the object and moving away from it like that. Okay, once you've drawn a free body diagram, then you're going to be looking at solving problems with that free body diagram. And the first set of problems that we're going to solve on free body diagrams are all going to be Newton's first law problems. And Newton's first law means that the acceleration will be zero. So remember what Newton's first law is. Newton's first law is that if an object feels no net force, then it will want to keep doing what it was already doing. So an object at rest will stay at rest, and an object in motion will stay at constant speed doing the same motion as it was doing before. If we want to phrase that mathematically, then we would say that if the net force on your object in the x direction is zero, then that means the acceleration is also zero in the x direction. That means I'll keep doing what I'm doing in the x direction. I'll keep going at constant speed in the x direction. If I'm already at rest in the x direction, I'll stay at rest. And if the net force in the y direction is zero, then my object will keep doing what it's already doing in the y direction. Its acceleration in the y direction will be zero. It'll be at constant speed in y, or stay at rest in y if it's already at rest. So that right there is actually Newton's first law, and that'll be the first sort of set of problems that we solve using free body diagrams. Will all be situations where the acceleration is zero in both x and y. Notice I've separated it into x and y. It's going to be so important with these forces to draw them in x and y separately. Don't try and draw them just like an overall net force. We're going to do all the forces in x, sum those up, and they add up to zero. All the forces in y, sum those up, and they also add up to zero. All right, so we'll start with one more thing. If the net force is not zero, then the acceleration will be in the direction of the net force. So that is actually Newton's second law. The net force is equal to the mass times the acceleration. So that's Newton's second law. And we'll spend some time solving problems with that in sort of the second half of our forces unit. We'll start with the situations where the acceleration is zero, so our net force will be zero. It's just a little bit simpler to start. Okay, let's start with a really easy problem, and we're going to solve this like super thoroughly mathematically, even though it seems like a really simple problem, so you can see what the process is that we're using. Okay, so Little Miss Sunshine is standing on level ground, so you want to draw level ground. It's helpful to draw the ground in your free body diagram. I find that just makes it easier. Here's Little Miss Sunshine. She's kind of like a ball, so there she is. Then we want to draw all the forces that Little Miss Sunshine feels. So not forces Little Miss Sunshine is exerting on her surroundings, right? Or not internal forces. If she's pushing on herself, we wouldn't draw that. We draw all the forces she feels from her surroundings. So the first obvious one is she's going to feel gravity. She's on the surface of the earth. She feels gravity. Gravity acts from her center, and it acts just straight down. Gravity will always be straight down if you're at the surface of the earth. And the symbol for that is capital F for force and a G meaning force of gravity. She also feels a normal force. So that's the reason why she doesn't just fall through the ground, is because the ground is pushing her up. Right? So she feels an upwards force from the ground that looks like that, and the normal force is Fn. The normal force is always 90 degrees to the ground, so notice that's a 90-degree angle. If the ground had been tilted, my normal force would also be tilted. Gravity is always straight down, but the normal force is always perpendicular to the surface. One more thing that every free body diagram needs, and this is true of every picture in physics, is a coordinate system. So we need to say that y is positive up and x is positive forward. All right, and that's my free body diagram. Okay, we're asked to calculate all the forces on Little Miss Sunshine. We know her mass. So if you know the object's mass, it's kind of a giveaway that it's probably a good idea to calculate the force of gravity. You can see from your coordinate system, if y is positive up, the force of gravity is down here. The force of gravity is going to be a negative value, and it will be negative m times g. Notice that mass is always a positive number. G is always a positive number, so I have to put the negative sign in here from my picture. That doesn't come from any equation, it just comes from my coordinate system and my picture. I'm plugging your numbers, so I get negative mass, which is 50, times g, which is 9.8. Toss that in, and you get negative 490 newtons. We'll round off to sig figs at the end, and just leave it for now. All right, your next step is to calculate the normal force. There's no nice simple equation for the normal force, though, like there was for the force of gravity. What we do to find the other forces is we use the fact that the net force in the y direction will be 0 if she's not accelerating. So this will be a step that you do in basically every single one of these problems. We're going to sum up our forces in the y direction. What we're looking for is what are all the forces that pull Little Miss Sunshine or push her either up or down vertically. And then we add them all up. So net force in the y direction means just add them up. So there's a normal force, so we write that one down. And there's a force of gravity, so we write that one down. This is a really simple problem. There's only two forces. It's really important to show this step. And then we notice, okay, wait, Little Miss Sunshine is standing still, right? So she's not accelerating at all. She's not even moving. She's at rest. And because her acceleration in the y direction is 0, in fact, her acceleration in total is 0, that means the net force in the y direction will have to be 0. We always have to write this in, so don't just plug in a 0 here for the net force in the y direction. We need to write something about, because her acceleration in the y direction is 0, Little Miss Sunshine's net force in the y direction will also be 0. We need to write that in because it's not always the case, right? If Little Miss Sunshine was maybe jumping upwards at this moment in time, then she would be accelerating, right? So she would not have a net force in the y direction of 0. But because she's just standing there at rest, her acceleration is 0. That means her net force in the y direction is also 0. That means I can plug in a 0 here for her net force in the y direction. And I get this, Fn plus Fg. If I want to solve for Fn, I just need to rearrange this. I can move the Fg to the other side, it becomes negative, and then I'll write the whole thing forward. So Fn is going to be negative Fg, and then plugging your numbers, so that'll be negative 490 newtons, which is just positive 490 newtons. So the normal force is positive 490 newtons. Last step, I should probably just round things off to sig figs here. So the force of gravity, looks like I've got two sig figs there. It's going to be negative 4.9 times 10 to the 2 newtons. And the normal force is positive 4.9 times 10 to the 2 newtons. Now this may seem like a fair bit of work here. This careful step of showing our net force is normal force plus gravity, saying that because the acceleration is 0, the net force is 0, plugging that in, and then rearranging for the normal force. It seems like a lot of work just to say that, well, hey, these forces have to balance each other out, right? Because she's not accelerating in the y direction, these two forces have to be the same size. So of course, if gravity is negative 4.9 times 10 to the 2, Fn will be positive 4.9 times 10 to the 2. That's true here, but I really want you to show this process because often that's actually not the case. We'll do an example, our third example, where there'll actually be also a tension force kind of pulling your object upwards, and the normal force and gravity won't just balance out. There's more going on there. We have to account for that. So I do want you to show this process every time. So always show this process. It will help you a lot and will let you solve much more complicated problems without making mistakes. All right, let's look at a situation where Little Miss Sunshine is accelerating. So what if she jumps off her chair and she's in free fall? We need her coordinate system here. Y is positive up, X is positive forwards. Here's Little Miss Sunshine. If she's in free fall, she only feels one force, and that would be the force of gravity. She's not going to feel a normal force because that would be a force from the surface she's standing on, and she's not standing on any surface, right? She's free falling. So the only force she feels is the force of gravity. And Fg is the same as before, negative m times g, or negative 50 times 9.8, which is going to be negative 4.9 times 10 to the 2 newtons. In this case, you can say that Ay is definitely not equal to 0. So therefore, that's my little therefore symbol, the net force in the y direction is definitely not 0. In fact, you can see this from your picture, right? There's nothing to balance out gravity here. The net force is going to be down. The net force is actually just gravity in this situation. All right, ready for a trickier example. I have to note, sorry, I forgot to put one thing in this problem, which is that the tension force is 150 newtons, but it needs to be at an angle of 30 degrees above the horizontal. Sorry, I didn't say that in the problem, but we're going to solve it that way because that makes it a more interesting and fun problem. All right, so here we've got a sled. It's got a mass of 22 kilograms. Being pulled with a constant speed of 1.3 meters per second. It actually doesn't matter what the number is for the constant speed. The fact that it's a constant speed tells me the acceleration is equal to 0, and that's really the important part from all that. Then we've got the tension force of 150 newtons. We're going to make that at an angle of 30 degrees above the horizontal. Sorry that I didn't put that in the original problem, so I'll just write that in here at an angle of 30 degrees, and I'll show you what that looks like in a picture in a second. First, we're going to draw the free body diagram of the sled, and then we'll calculate all the forces that act on the sled from that free body diagram. So our overall process that we're going to use with this problem and with any problem is always start by drawing the free body diagram out. And then if you can, calculate gravity. It's just not a bad idea. This is only if possible. So you can't always calculate gravity. If you don't know the object's mass, you can't calculate the force of gravity. But it's just so simple to do a little, Fg is m times g calculation, right? If you know the mass. So not a bad idea to do it if you can. But if you can't, just move on, skip that step if you can't. Then look for any force that's at an angle. So that's why I wanted to put the tension force at an angle here to make this more interesting. Then it's not parallel to x and y, and we split it into its components. We're going to use SOHCAHTOA for that to split into components. Next, here's the step that we'll do every time here. We sum up all the forces in x. So we find out what is the net force in x, and we just write down all the x direction forces. Then we sum up all the forces in y. So we find out what is the net force in y. And we check if the acceleration is 0 in the x direction, we make the net force in the x direction 0. If the acceleration is 0 in the y direction, we make the net force in the y direction 0. And these two steps here, this lets us solve for basically all the forces that we don't know. So this lets us solve for the forces we don't know. So there's really only one sort of traditional equation that we need here. The force of gravity is mg. All the other forces, the normal force, we'll get all of that. The friction force, those will all come by summing up the forces in the x, summing up the forces in y. That's how those will appear. All right, let's give this a try. So we need our picture here. First, I'm going to do my coordinate system. So y is positive up, x is positive forward. Here's the sled. It feels the tension force, and I'm going to draw that tension force here. So that's Ft for tension, but I'm drawing it at an angle of 30 degrees. So that's a 30-degree angle here, just to make this problem a bit more interesting. The sled, of course, feels gravity too. So Fg. And it's not falling through the ground, so it must be feeling some sort of a normal force. So there's Fn. And it's a sled, so it's going to feel some friction backwards. The friction will always be parallel to your surface. Oh, there we go. And so it'll be pointing backwards to oppose the slide. So if it's sliding forwards, the friction will oppose the relative motion between the sled and the snow. That's going to make a backwards friction force. And it's sliding, so it's a kinetic friction force. So we can call it FFK. All right, there is our lovely free body diagram. Let's dive in. So our first step is, if we can do it, let's calculate gravity. And in this case, we can. So I'll do that first. So Fg is going to be negative mg, and I'll toss that negative in right away because I can see from my picture y is positive up, g is definitely negative. So that'll be negative the sled's mass, which is 22 kilograms times 9.8. And don't worry about sig figs yet until the end. We get 215.6 newtons for the force of gravity. At this point, actually, I can't solve for like any other forces right away, right? I have to start splitting things into components here. So my tension force has a component in x and a component in y. So split that tension force up into its x component and its y component. That right there is Ftx, and this is Fty. Don't forget to put arrows on them. The tension force is this way, so my x direction force is going to be forward, and the y component of that tension force is going to be up, because overall that vector is sort of forwards and up. We need to calculate what those are, and we can use SOHCAHTOA for that. So Ftx, and I think actually I'll calculate these in a nice chart just to organize things. So here's x stuff and here's y stuff. Let's kind of get it nice and organized. So Ftx, it's going to be your overall tension force, and it's close to my 30-degree angles here, so I'll do cos. So Ft cos 30. You can plug in your numbers. Tension force is 150. It's cos 30, and that gives me 150 times cos 30 is 129.9 newtons. It's positive because that vector is forwards, right? Let's do Fty now. So the y component of the tension force, also going to be positive. It'll be Ft sine 30. So here we've got our 150 times the sine of 30, which is 75. Positive 75 newtons there. Let's organize our other forces in this same XY chart. It's really helpful to know what is your x direction forces, what is your y direction forces, so that we can sum them all up. So gravity was a y direction force. So Fg was this negative, sorry, I didn't have my negative sign there, negative 215.6 newtons. Sorry about that note from before. There should be a negative there, right, because gravity is down. Not sure why I dropped that. Other forces that are in y, there's a normal force in y, but I don't know what it is. I'll just write it down with a question mark. In x, there's also this friction force, FFK, but I don't know what it is, so I'll also write it down with a question mark. Now, to calculate these last two forces, your FFK and your normal force here, what we're going to need is summing up our forces in x and y separately. So I will just get rid of this here, so I've got some more space. So let's start by summing up our forces in the x direction. So my net force in the x direction, and I look at, well, what are all the x direction forces? There's Ftx, that's the tension, but just the component of the tension in x. I don't want to use the whole 150. I'll just use the x component of that. And then there's the friction force, and the friction force is fully in the x direction. You can see that's totally a horizontal force there. Then I can say that, well, I know that the acceleration of this sled in the x direction is 0. That's because we're told the sled is moving at constant speed. So therefore, my net force in the x direction will also be 0. So I can plug in a 0 here for the net force, and that will equal Ftx plus my FFk, the friction force. This lets me solve for the friction force. You can see the friction force here is going to be negative of the tension force. So let's put that in here. That friction force is actually a negative of your tension, the x component, specifically just the x component of your tension force. So negative 129.9 newtons. Next, I can start summing up my forces in the y direction. So I'll just erase this so I have more space again. So in the y direction, my net force, there are 3 y direction forces. So there's the normal force, there's gravity, but there's also this component of tension, Fty. So this is more complicated than the question we did with Little Miss Sunshine a couple of minutes ago, where gravity and the normal force just balanced out and were the same value. Here, I definitely could not say that the normal force is just positive 215. It's not. It's going to be smaller than 215.6 newtons. And that's because there's sort of 2 things balancing out gravity. The tension force component, the y component of the tension force here, and the normal force are working together to balance out this force of gravity. That means the normal force will not be as big as it would be otherwise if the tension force weren't there. So this is why it's so important not just to write down, oh, normal force and gravity are the same size. They're often not. Often is a situation like this. All right, so we can do our little move where we know that the acceleration in the y direction is 0. So this lead here is not even moving in the y direction, right? It's just moving horizontally. So that means definitely the acceleration is 0. So that means the net force in the y direction is also 0. So you can plug in a 0 there. 0 will equal your normal force plus gravity plus Fty. I already know gravity, and I already know, so that's a G. I already know gravity, and I know the y component of my tension force already. So all I have to do is rearrange this for the normal force. So that means I'll subtract Fg on this side, subtract Fty, and I get the normal force is negative Fg minus Fty. So it's going to be negative, and then plug in the value for Fg. So negative 215.6 minus Fty, which is 75. And that gives me, so negative makes a positive there, so positive 215.6, and then minus the 75, I get 140.6 newtons for my normal force. So I'll just erase that a little bit there. My normal force must be 140.6 newtons. All right, so with that, I've got all of my forces. My last move is just to write them all down with the right sig figs. I'll just erase this to give myself more space again. There we go. So my first one here was the force of gravity that we solved. And it looks like I have 3 sig figs here everywhere, so I need to write it down to 3 sig figs, so it'll be negative 216 newtons when I round that off. The next one is the tension force, and I'm actually just given that one in the problem. The overall tension force is 150 newtons. We already found the components from writing down all the forces, then I just get to write the overall one down there. The next one is the normal force here. The normal force we calculated to be 140.6 newtons. I'm going to round that off to 3 sig figs, so that'll be just 141 newtons. And the last force is that friction force, and it's a kinetic friction force, FFk. It's negative because it's backwards here, and we get negative 130 newtons for that one. And that is all the forces acting on the sled.